Okay, welcome to the second half of our lecture on RLC circuits, including their impedance and phase angles and resonant frequencies. Okay, so in this second half of the lecture, we're going to start by looking at our key equations. So here we are on page 5 of lecture 13 for material that will be included on exam 2. Okay, so if we look at our diagrams up top, these are really similar to the diagrams that were on the previous page, the page that included the key terms. These are just showing the phasors again. All right, so we've got our voltage across the resistor, voltage across the inductor, voltage across the capacitor. We've got our appropriate phase angles, one positive for the inductor, one negative for the capacitor. We see then here that we've got our phase angle clearly shown with our right triangle. And so this does a good job of showing exactly how you would calculate the phase angle, because if you know two sides of the triangle, for example, you can find theta, or if you know theta in one side of the triangle, maybe you can find the hypotenuse and so on. So you can imagine any combination of questions based on that material. But I've included this whole diagram in particular because of part C, because part C points out that we can make another similar triangle just being a triangle that has equally proportioned sides. And in that case, instead of having the voltage across the resistor, the combined voltage across the inductor and capacitor, and the overall voltage of the RLC circuit as our three sides of the triangle, instead we've got the resistance across the resistor, the combined reactance across the inductor and capacitor, and a value Z. Well, Z represents the impedance of the circuit, the overall impedance. All right, so this is the impedance of the RLC circuit. So you can really see then that one of the things that we might want to calculate is the overall effect that the circuit has on slowing down the current, choking the current. That value measured in ohms, represented by the uppercase letter Z, is the impedance. And we can clearly see the right triangle that we'd use to find it, or at least maybe work with it. All right, so let's get right to our equations. So our first equation here is defining the total voltage in our circuit. So this is the RLC voltage. Okay. And this would be the RLC voltage amplitude, because that voltage is going to vary in time, because the whole thing about these vectors is they can rotate, as I hopefully elaborated on in the first video. But the maximum value would be the value represented here. And that's the same value that shows up here in the right triangle. Okay, and that's often the one we care about. If we do want to do a time-dependent value, then we can do a projection. But let's look at how we do that. Well, we'd find that maximum voltage by simply using the Pythagorean Theorem. All right, because if you think about it, this here represents one leg of the triangle, one side of the triangle. This is the other side of the triangle. And together, when we sum up those two sides, take the square root of them, we get the hypotenuse. Okay, so that's why I included the picture again on this page to clearly show where it's coming from. Okay, so let's show that. Okay, but then as I just said, we can take the same idea and extend it to impedance. All right, so there's impedance. Okay, and then impedance is going to be using the Pythagorean theorem again, but in this case with the resistance and reactance. Okay, so there it is right there. And then I also want to remind us about what the impedance looks like, or rather the reactance looks like, used to calculate the impedance, but what the reactance looks like for the inductor and the capacitor, because we've only seen that a couple times. So if we take a look, we'll write the values over here. So the reactance of the inductor, since it's first, is going to be 2 pi FL. And then the reactance of the capacitor is going to be 1 over 2 pi FC. Okay, so 1 over 2 pi FC. Okay, and I'll just briefly mention again that the key idea behind both these formulas is that reactance of either of these circuit elements, the inductor or the capacitor, is frequency dependent, and that we've talked physically about why that is, having to do about how capacitors charge and discharge and slow down the current as they do so, and how the inductor creates a back EMF, but only when the change in the current is greatest, which is going to occur when, say, a circuit is first, when the change in the current is maximum. So that could be when a circuit is first opened or closed, but for an alternating circuit, it's just going to be wherever the slope of the sine function or cosine function is steepest, which occurs as you cross over the axis, right? Because it's the max and minimums for a sine function have not steep slopes. In fact, they approach a slope of 0. Okay, so looking at it also, we can see that, high frequency makes for high inductive reactance, and and high frequency makes for low capacitive reactance, and vice versa for high frequency. Okay, so hopefully that all makes sense. And then we'll move right on to looking at the phase angle. Okay, so this is tangent of the phase angle, the way that you'll generally see it. So here is the phase angle. Okay, and again, the phase angle is just the name given to the angle that is defined by the sides of the triangle, as mentioned before. Okay, so then the tangent of the phase angle would be opposite over adjacent. And so the opposite side of the right triangle is the difference between the voltages of the inductor and capacitor, and then the adjacent side of the right triangle is the difference in voltage, or the voltage across the resistor. Okay, this side of the triangle and this one. Okay, and then likewise we can then go over, and obviously we're not proving this transition here, but we can make using the definitions, we can replace the voltages with reactances. So in this case, it would be a ratio of values measured in ohms, right? Because all three of these terms are measured in ohms, whereas here, all the values are measured in voltages. Ultimately, that means in both cases, since it's just a ratio of values, there's no units in either of these expressions. But of course there can't be, because when we're doing an angle, then it always has to be unitless. Okay, all right, so hopefully that all makes sense about in practice how you would calculate the phase angle. And then we've got a couple more formulas down here. So this is just showing how to use Ohm's law for an RLC circuit. So this is Ohm's law for an RLC circuit. So a couple ideas we've seen before, but now just extended to our RLC circuit. And I should really say these are ideas we saw in particular for for circuits that included alternating circuits that included just a capacitor, or alternating circuits that included just an inductor, discussed in the earlier half of chapter 21. But here, for a circuit that includes a capacitor and an inductor, and in all cases a resistor as well, we have, instead of having the reactance multiplied by the current, we have the impedance represented by Z. Okay, and there's two cases here, because this top formula just shows the case for maximum. So that would be the amplitude of the voltage equals the amplitude of the current times the total impedance of the circuit. And then here we have the RMS value times the RMS value, so the root mean square, times the total impedance of the circuit. All right, and we got one more formula here. This is how we calculate the average power. I'll leave it over here. So this is the average power output of the circuit. Okay, and then this is the aforementioned power factor. So the key idea here is that it turns out that the average power is affected by the phase angle. So it's affected by essentially how close or how far apart the reactances of the inductor and capacitor are. Because now let's talk a bit about the phase angle, because we're going to talk about one important conceptual and computational way it's applied. Well, let's think about it. So the phase angle is 0 whenever the reactance of the inductor equals the reactance of the capacitor. Okay, so I'll make a note over here. So note that phi equals 0 degrees when the reactance of the inductor equals the reactance of the capacitor. And the big consequence of that is that if we have a phase angle of 0 degrees, then we're going to have maximum average power. So note that P average equals maximum value, or I'll just say is at maximum. So is maximum when cosine of phi equals 1, which corresponds to phi equaling 0 degrees, which corresponds to the reactance of the inductor equaling the reactance of the capacitor. So if we want a circuit to be operating at maximum power, we want to have balanced the reactances of our two frequency-dependent circuit elements, the inductor and the capacitor. And then the final idea of balancing a circuit, of having the reactances equal to each other, the reactance of the inductor and reactance of the capacitor, is encapsulated in the concept of the resonant frequency, because the resonant frequency is the frequency that achieves maximum power output. So this is the resonant frequency. And which is max power output. Okay, and of course I mean max average power output, but it basically is making this term as big as possible. That's where it's resonating. That's where the circuit's doing the most, because it's running at its highest possible power rate. Okay, and where does this expression come from? Where do we get this whole 1 over 2 pi times the square root of L times C? Well, it's from simply setting the two formulas for reactance equal to each other. So that's it. So we can say that this is then derived from, and it's a simple calculation, but it's derived simply from 2 pi FL equaling 2 pi, or 1 over 2 pi FC. Okay, and then just solving for F. And you can see what would happen. You'd cross multiply by F, get an F squared, and then just go from there. All right. Okay, so those are all the formulas that kind of bring into focus the ideas that were presented in the key terms in the last video. So formulas for impedance, formulas for phase angle, formulas for average power, and resonant frequency being the big takeaways. Okay, actually let's go ahead and underline those in red. All right, so impedance, phase angle, average power, resonant frequency. Okay. All right, so let's get to our first example. All right, so in this first example, we're just going to look at a basic RLC circuit and find its impedance. Okay. So in this case, we weren't given any of the reactances, but we were given the impedance and the inductance and the resistance. So we can go ahead and calculate our reactances and thus calculate our impedance. So pretty straightforward here. We just need to identify the correct formulas to use, really. So what I'm going to do is I'm just going to identify that R is just equal to 50 ohms. So that's going to be given. And then let's find the reactance of our inductor, just reading from left to right. So the reactance of the inductor is going to be 2 pi F times L. Okay. So in this case, that would be 2 pi and then times 50 hertz. Okay. And notice F in this formula is frequency, not angular frequency, so we don't have to make any conversions. And then we'll multiply by the inductance, which is given as 0.2 henries. Okay, so that's going to be our reactance measured in ohms. Calculate in a second. I just want to set up the capacitance one as well. And so that one is going to be 1 over 2 pi FC, which will be 1 over, and then 2 pi 50 hertz times 150 times 10 to the negative 6 farads. There we go. Got it to fit. Okay, and so let's get both our values here. Okay, so 2 pi times 50 times 0.2 for the inductive reactance. I get a value of 62. Basically, we'll just do 2 sig figs as we're working with there. So it'd be 63 ohms. All right, and then for the reactance of the capacitor, let's see, so 2 pi in the denominator times 50 and then times 150 times 10 to the negative 6. Okay, and so that gives me 21.2 or 21 ohms. Okay, so there we have it. All right, and then we want the total impedance. So then the total impedance based on our phasor diagram and the right triangle formed by the resistances and reactances, we now know is R squared and then minus or plus XL minus XC quantity squared. All right, and we can plug in our numbers. Okay, so then we're going to have our 50 ohms right here And then we got our difference, so 63 minus 21, and then ohms, square that expression. Okay, and there it is, the impedance of our RLC series circuit. But anytime I say RLC circuit, it's always going to be series. Okay, so 50 squared, and then I'm taking my unrounded values from the calculator, putting them all in, and then we end up with a total impedance of 65 ohms. All right. So in this case, the impedances of the inductor and the capacitor don't have a big effect because the resistance is higher, right? But it does show up. It goes from 50 to 65, so I shouldn't say it's not a big effect. Okay, all right, so there's our first example. It's pretty straightforward, but definitely good to see the equations in practice. Okay, so let's take a look at another example here. We have a circuit that has a 58 ohm resistor, a 0.4 Henry inductor, and a 10 microfarad capacitor. They're connected in series to 106 hertz. The RMS current in the circuit is 3.99 amps. What is the phase angle of this circuit? And what is the average power dissipated by the circuit? Okay, so quite similar, but I'm going to work through the steps here. Okay, so just to show, because we haven't seen phase angle or power dissipated. Okay, and so first of all, we do need to find Z. So I'm going to do something quite similar. Maybe I'll do it in one step this time. So we'll set up the square root like this. Okay, and then we're going to have my R squared and XL minus XC quantity squared. All right, and let's plug in all our values in one swoop. Okay, so we have 58 ohms, and we're going to square it. And then over here, I'm going to have 2 pi times 106 hertz times 0.4. Okay, and then I'll subtract 1 over 2 pi. Okay, so then we got 2 pi times 106 hertz, and then times 10 to the 10 to the negative 10 farads. Okay, finish that off. And then let's put in our square and close off the square root and everything. So let's bring this over just a tiny bit. Okay, all right. So all inside the root, and then this should be squared. There. Okay, so there we have calculating the impedance in one step. It's for a change. Okay, so we have 58 squared, and then we'll open up the root and everything. All right. Okay, so I get a total impedance. Once I check the form on my calculator, everything checks out. I have all the squares where I need them. Everything's inside the root. Okay, so I end up with 130 ohms. Okay, so that's my total impedance of the circuit. And so then I was asked for the phase angle. Okay, so let's see. I actually could have gotten away with not calculating the total impedance, so my bad. But let's go ahead and do the phase angle. So then the phase angle is then going to equal just the XL minus XC divided by R. Okay. Oh, but of course tangent inverse of all that. Right? Otherwise it doesn't make any sense. Okay. So I'll have tangent inverse of that expression. All right, and let's go ahead and actually get our individual numbers, because we will need them, the individual values for reactance. So if we take a look, the reactance of just the capacitor, let's see what I have for that. That one is 150, and then the reactance of just the inductor, so 106, and then times 0.4, that one's 402, okay? So then we would have tangent inverse and 402 ohms minus 150 ohms, all divided by 58, okay? So 58 ohms, the resistance, okay? And so then our phase angle is then going to be, let's go ahead and do the tangent inverse of that. Okay, so I have my 402 minus my 150 in the numerator. Okay, and then divided by the 58, all inside the inverse trig, gives me an angle of 77 degrees. Okay, so a pretty steep angle, and that's because a lot of the impedance is actually happening due to the inductor, and really the inductor, and the canceling effect of the capacitor is not that significant, and so we really see the inductor as the major player here, giving us a big phase angle. Okay, and that big phase angle means that our power is really going to be significantly lower, right? Because having our phase angle be so large means that we have cosine of something that's approaching 90, right? 77 being close to 90. If we did have 90 degrees, then we'd end up with a circuit that really wasn't outputting any power or couldn't output any power. And we could never get all the way there due to the way the functions are defined, but we could get it to be like 89.9 or something, okay? But let's go ahead and actually find that average power. And again, I just want to clarify again that I didn't need impedance in this particular problem. I calculated it, but it was not asked for. So part B, what is the average power? So we can definitely quickly answer this. So we have that P average is then going to be, let's flip back to the formula here real fast. So it's just IRMS and then delta VRMS. Okay, so IRMS. Oh, and actually I may have a use for that overall impedance after all. And then I'll multiply by the power factor, so cosine of phi. Okay, looks good, looks good. So we were given the RMS current, the 3.99, but I realized that we weren't given the delta V RMS. So that's where I'm actually going to put this into use, because then I can find delta V RMS with Ohm's law. So I'll write over here that delta V RMS is then going to be, and this is using this formula here, I'm going to use Ohm's law. Delta V RMS is just IRMS times Z. So now we really have a use for having calculated it. It's pretty cool. So IRMS times Z. Okay, and so then that's just going to be our 3.99 amps multiplied by our 130 ohms. I'll take the unrounded values, but that's our delta V RMS. So let's see what we get for that. So 3.99 multiplied by impedance of 130 gives me 518 volts. Okay, and so that means that our power factor will be our 3.99 amps, that's our VRMS, or our IRMS, so our root mean squared current, multiplied by our root mean squared voltage, which is 518 volts, okay? And we could find the maximum values because we know that we just multiply by root 2 in order to get the maximum values. Okay, and again, that just referred to the definition of root mean squared for that. And then I'll multiply by cosine of 77, right? 77 degrees. And that is going to be our power, our average power output, which will be measured in watts. Okay, so let's bring all our numbers together. So 3.99 times the 518 voltage, root mean square voltage, multiplied by cosine of our angle, and we get 464 watts. Okay, so cool. You can really kind of see how you can answer these questions and get your circuit elements to all work together. Okay. All right, so let's see what else we want to take a look at here. So we have a couple other examples. Some I will just leave for further practice. But let's take a look at our concept question before we wrap things up. So in an RLC series circuit, the source voltage is leading the current at a given frequency f. If f is lowered slightly, then will the circuit impedance increase or decrease? Okay. So what's going to be happening if we slightly decrease f? So the source voltage is leading the current at a given frequency. So let's see. Okay, so we have, if we think of the overall impedance increasing or decreasing, we have to kind of think about what's going to have the bigger effect, the reactance or the capacitance. So let's think about how we would define that. So we have our impedance with our R squared, and then minus XL minus XC squared. Okay, and so perhaps we want to think about, well, the voltages and their effect, or kind of think about it, I think maybe thinking about it in terms of the phasor diagram. So if we have, so by having F, so if F is, let's see, so if F is lowered, then that's going to make our XL go down. So as F goes down, the impedance on, or the reactance on inductance also goes down because they're directly proportional. And as the frequency is lowered, the impedance on, the reactance on the capacitor goes up. And remember, because that's because reactance in the capacitors is inversely proportional to the frequency. So as frequency goes down, it gets, the reactance gets bigger and bigger. Okay. Yeah. Okay. So we can definitely see what's happening then. So by lowering the frequency, this term's getting smaller, this term's getting bigger, which means that this difference is, so that means, oh, that should be a plus. That means that this term is becoming smaller. So we can say thus XL minus XC becomes smaller. Okay. And therefore, impedance decreases because resistance is unaffected. So just making this second term smaller means that the overall impedance is going to decrease. All right. All right, and so our last two ones here, an RLC circuit or RLC series circuit with a given inductance, capacitance, and frequency is, and then we're told the phase angle and we're asked for R. So you can think about just taking the phase angle and solving for R. Right, so you just use the formula for phase angle, but instead of using inverse trig to solve for theta, you would actually just solve for the R value in that expression. Okay, and then example 4, an AC series circuit contains a resistor of 30 ohms, capacitor of 100 or 1.22 microfarads, and an inductor, right? So we're often given those three values. And what frequency should be used to create a resonant condition in the circuit? So that one is pretty straightforward in effect, because we essentially just want to find the value of the resonant frequency so that the reactances of XC and XL are equal to each other. Okay, well, thank you for listening to these videos. And if you have any questions about the topics of an RLC circuit, the ideas of phasors, or even earlier ideas from chapter 21, including the ideas of reactance and the concept of leading a circuit and the reactance leading or falling behind the current, the voltages, leading or falling behind, any of those concepts, even the concepts of root mean square, all this new material, please ask me about it today. All right, thank you.